Welcome to Computer Networks. This is lecture 21. Just wanted to remind you that there is a homework due this week. You haven't gotten the user IDs so far, right? And how to log in, so this is what that is about. You're going to get that after, towards the end of this class. So we're going to talk about that. And there are some student presentations. There are two of them later today. All right, let's talk about homework for a few minutes. If you already got a chance to look at it, if you have some ideas on what you might do, let's discuss that now. And make sure you get a user ID before you leave the class, because you will need a user ID to log into these machines. So any thoughts, any concerns about the homework? Who read it? Okay, just half of you read it. Did it seem challenging or easy, or something doesn't make sense? No comments. Okay. Well, we can discuss it more on Wednesday. One thing I would like to tell you is it might be a good idea to learn something called GraphViz if you haven't already used it. Because one of the questions asks you to draw a network with edges proportional to the latency that you measure. And it's going to be kind of hard to do it manually. If you use tools that allow drawing graphs, that'll make it very easy. Did you use any drawing tools in your algorithms course, for example, to draw graphs? No? Okay, so it might be a good idea to learn how to use it. It uses if you decide to use that particular tool, there's a very simple language that you have to use to describe a graph, and you provide this text description of a graph to the program, and it draws it.
What was the name of the tool?
It's called GraphViz, as in visualization. The name is listed on the homework. What's that? Yes. So I would just, if you don't have time to do the measurements immediately, or if you don't want to, that's another thing that'll be helpful, and you will need to know how to do that anyway. And you can SSH to these machines using user ID and password. That will give it to you first in this class. Any questions before we proceed? All right. Today we're going to talk about wireless networks. Okay. Why do we want to talk about wireless networks? Well, we use it everywhere these days. For example, my laptop is connected to the internet using wireless networks. Could you close the door? And you probably heard some of these phrases. You've got 11, 3G, 4G, WiMAX, Bluetooth, RFID. They're all different wireless technologies, right? And maybe you haven't heard of the second set of names, sensor networks, Internet of Things. Have you heard of these? So it's for example, sensor networks is the idea that you can deploy a lot of sensors all around where you live. And if you want to do that, it's probably not feasible to wire each sensor. So that would be one place where you might want to use wireless networks. So let's say we want to sense climate, let's say in all the rooms in this building. We could do that using wired networks, but from deployment perspective, it might be a little bit easier if we use wireless networks. Right? So those would be sensor networks, network of sensors. Internet of Things, those are more general than sensor networks. For example, we might connect all of the appliances and equipments at homes to the internet. If we want to do that, of course, we can use wired networks, right? For example, if we want to connect a refrigerator, microwave, stove, dishwasher, etc., to the internet. We could do that using wired networks, but it would be easier if we used wireless networks. So a lot of the Internet of Things type devices are connected using wireless networks. And here's an interesting trend. A lot of the new computers, they have no wired networking. For example, my laptop does not have a port for a wired networking. I need to buy a separate USB device if I want wired networking. a lot of the netbooks and Chromebooks, if you've heard of those phrases, they probably don't have a wired port by default. So that's sort of the trend these days. So we're going to try to learn about a few things that make wireless networks work. We've spent a lot of time studying networks. They were of the wired variety until now. And maybe the best way to learn about wireless networks is by understanding how they're different from the type of networks that we've been studying so far. One of the differences is how the signal changes with space and time compared to wired networks. In wired networks, of course, there are some packet drops. There is some signal attenuation, but in wireless networks, much more pronounced than in wired networks. Have we all experienced signal attenuation in wireless networks? You probably have. Right? For example, you might monitor the signal strength of access point at homes using this 5-bar system or whatever you might have. And if you move closer to the access point, sometimes you might get better signal, better connectivity. Right? We've all experienced this. In wired network, we typically don't see that. Right? Once you have a wire of certain length, just making it shorter does not necessarily make the network work faster or better in one way or another, as long as that wire meets the specifications. So we've all experienced this, right? So that's different about wireless networks. And when we design systems to work in wireless networks, we have to keep that in mind. We can't just use protocols that are designed for wired networks. If we forget some of these facts, it's just going to break. Another aspect of wireless links that's different from wired links is variation over time. And again, this is something that we've also experienced in daily lives, right? For example, if you have a cell phone, sometimes it works, sometimes it doesn't. Just variation over time. Same with wireless networks. It was working perfectly fine when my laptop was here yesterday. Now it's not working anymore. So we see the significant variation in time, much more than in wired networks. And finally, in wireless networks, it's harder to know what's happening at other nodes if you wanted to coordinate communication between the nodes than in wired networks. And we'll see an example of that. And finally, here's the biggest difference. Wireless medium is inherently shared. Remember we talked about shared medium in Ethernet, and what did we say is the way in which most of the corporate networks are designed today? Do they use shared Ethernet? They don't. They use switches, right? And why do we like switches? Why do we like switches?
Because it avoids all the overhead involved with shared medium.
Yeah, so we're basically isolating the medium, right? Rather than just having one shared wire connecting all the computers, we have each cable connecting a computer to whatever it needs to talk to using a switch. So that whenever a computer needs to send a packet to the destination, you don't have to contend. What that means is you don't have to coordinate with another computer saying, okay, is it my turn to send or is it your turn to send? You have a dedicated media to the destination, being the local area network here, right? And that's the reason why a lot of the corporate networks now use switches. But it turns out in wireless networks, they're back to shared media. Why can't we have switches in wireless networks?
Because that would entail making like a separate chunk of bandwidth for every separate port on the switch.
Yeah. So you could emulate something like a switch in wireless network, as you suggested, but more generally, there's just one access point, and there are a number of us that are in the same physical world, and we need to just share the medium, right? It's just like sharing the air we breathe. We can't just create a separate chunk of air for us to breathe, right? So all of the computers, they are trying to use a shared frequency band for communication, so they will just have to contend. So does everyone understand this difference? It's a shared media. So what are the implications? We need different mechanisms across the layers if we want protocols to work in wireless networks. We can't just use what worked in wired networks. For example, in the physical layer, if we wanted to adjust various properties of the hardware that modulates and demodulates the signals, because they are different, the tuning of these hardware might also be different. For example, we might talk about transmission power. We don't typically talk about that when we're talking about wired networks. If you have gone into the control panel of the routers or wireless access points that you have at home, you can set transmit power. Have you seen that? Some of the routers actually allow you to do that. So some of the adjustments that we might make in wireless networks, they don't make a lot of sense in wired networks. Just wanted to give you an example of that. Similar link layers are going to be different. We'll go through an example later today. And upper layers, they're also going to have to be modified to make them aware of wireless networks. And a lot of the new work in wireless networks, they do not abstract away some of these physical and link layer properties of wireless networks. In the earlier days, we just treated wireless links as just like any other link. And protocols work to some extent, but if you really want to get a good performance on these networks, it turns out you cannot abstract away some of these details. So let's get into the details of some of these unique properties of wireless networks. So the first thing that is worth discussing, because this is a pretty important part of wireless networks, it's interference. When one device is trying to transmit a message to another device on a shared spectrum, that transmission might experience a variety of interference. What that means is some energy emitted by some other device is going to interfere with this transmission. For example, when we have two laptops that are trying to talk to the same access point, sometimes when one access point, let's say one access point is transmitting messages to an access point and receiving a bunch of messages from it, transmission from another access point, another laptop could interfere with the transmission from the first one, right? And again, this is something we've experienced to some extent. For example, if you go to a crowded space, and if everyone is trying to use Wi-Fi, what happens?
Wi-Fi gets really slow.
Yeah. So there could be two reasons why it gets really slow. Can you guess what those two reasons might be? There are two reasons. So one is, one is interference. It's just the fact that there are too many devices that are trying to talk to each other or trying to talk to a particular device at the same time. So that's one reason. Another reason, which is nothing to do with the wireless network, which is the bandwidth at the access point might be limited, right? For example, if you go to Starbucks, they have internet service at their store, but that internet service is not going to have unlimited capacity. Right? So it's going to have finite capacity. Why does it have finite capacity?
Because it's not in there. It's not worth it for them to
Right.
buy a huge pipe.
Right, it costs more money. If they want to get a fatter pipe, you need to spend more money. So they have limited bandwidth, so that's the second reason why wireless network might get slow. But the first reason is interference. There could be different types of interference. First of all, could be interference from the same type of devices like we talked about. Right? When there is one laptop trying to communicate to the access point, another laptop trying to do the same thing and causing interference. Another is different types of devices. Do you think, let's say, when you have a laptop trying to send a message to an access point, trying to access a web page, if you use your smartphone, could that lead to some contention in the channel? channel is just another way of another word that describes the wireless media over which we transmit energy, which encodes information. Have you experienced that or no? Let's say you try to use, so we're convinced that if we try to use laptop and laptop, that could cause interference. How about if you try to use a laptop and a smartphone?
A smartphone over Wi-Fi? Or?
Yeah, so actually many smartphones, they also have Wi-Fi interface. They also support Wi-Fi. In which case, even though the devices are different, it could still cause contention. Right? How about Bluetooth? It turns out Bluetooth also operates in the same frequency band as Wi-Fi. So what that means is if I have a laptop and if I have a Bluetooth device, there is a potential for interference. Have you heard of something called Zigbee? That's a wireless standard for low power, small devices, Internet of Things or sensor network type devices. Turns out they also operate in the same band as Wi-Fi, the older Wi-Fi, 2.4 gigahertz band. How about microwave ovens? That's not a joke. It turns out that could cause interference. You should try this experiment at home and report your findings on Wednesday. Take your laptop very close to the microwave.
Melted my laptop.
You don't need to put your laptop. You don't need to put your laptop inside the microwave. But run the microwave and bring your laptop really close to the microwave. You'll see the difference. So why don't you do this experiment and I want to hear what you find. Okay? Don't cook your laptop. All right. There could be interference from external sources and just noise from the environment if there is energy in the same frequency band that you're trying to use for communication. All right, so we're going to discuss the wireless link layer first, and then if we have time, I will briefly also describe some of the routing issues in wireless networks. Okay, first of all, let's recap what we know about medium access control, or MAC protocols. If there is just one transmitter and one receiver, of course we want to give 100% of the capacity to that user, right? Because we want an efficient use of the channel. What if there are more than one users? What is desirable? We want to be fair with some definition of fairness. There are various definitions of fairness. Just to give you a flavor for the types of definition of fairness, for example, some devices might have very minimal requirement in terms of data rates that they need, in which case it would not be very efficient to say we're going to have equal allocation of bandwidth to all the devices. This doesn't make sense, right? So fairness does not mean equal. Keep that in mind. And there, you could come up with your own definition of fairness. There's something called max mean fairness, et cetera, et cetera. So one of the differences between what we learned about wired networks and wireless networks is how the nodes detect collision. So let's go back to our discussion of Ethernet in a shared medium. Who detects collision in Ethernet?
The sender.
So the sender detects collision in Ethernet, right? For example, you're transmitting messages, and we make sure the messages are long enough. Why is that? Because if there are any other transmissions that are happening at the same time, we want our transmissions to be long enough so that we know that our transmission might have gotten garbled, might have collided with some other transmission, right? So the collisions are being detected at the sender. It turns out in wireless networks, the collisions actually happen at the receiver. But that's the collision that matters, not the one at the transmitter. It's exactly the opposite. So the approach that many protocols try to use is avoid collisions in the first place, because it turns out detecting collisions at the receiver is hard. So we're going to illustrate that with some examples now. Let's imagine we have a 3-node wireless network, A, B, and C. And we want B and C to send some messages to A. So here A could be your access point. Right? Let's say A is your wireless access point, and B and C are laptops. Right? And when you need to browse a web page, you need to send this GET request to the server, right? So you're actually sending messages to the access point. So if you look at this topology, we realize that A can hear both B and C because they're within the range. The shaded ovals, they illustrate the range of the transmission. But can B hear from C? No. How about C? Can C hear from A? Probably. How about can C hear from B? No. But here's the problem. They can both interfere at A. So B cannot hear from C, C cannot hear from B, but they can both interfere at A. So there's a terminology to describe this scenario. So we call B as a hidden terminal to C. Basically, from B's perspective, C does not exist. And from C's perspective, B does not exist. Right? Because they can't hear from each other. So let's imagine using the same type of MAC protocols that we talked about in wired networks, which is the transmitter tries to detect if there is any transmission going on in the wireless network, right, or in the network. And that's called, what is that called? We use a word for that. What is that process called?
Collision detection.
Or carrier sense. First to see if the channel is clear or not, and then collision detection. So if we use the same algorithm, will it work? So let's say B says, okay, well, we don't want to have collisions. So what we're going to do is before we do a transmission, we're going to check the channel to see if it's busy or not. Busy means there is a transmission going on, and idle means there is no transmission going on. Will that algorithm solve this problem? No, it will not, right? Because from B's perspective, there is no transmission going on. Because C's transmission never reaches B. So carrier sense at sender is not useful. Okay, so that's one problem. Here's another problem. Let's say we have one more node. So we have a 4-node wireless network. Let's say A transmits a message to B. C is also going to receive it, because we're assuming they're in range. Now let's say C actually had packets to send to D. So how should C respond? So A is transmitting messages to B, and C had some packets to send to D. But C hears transmissions from A because they're close to each other in range. It turns out C is going to sense the channel and determine that the channel is busy. It's not idle. And normal behavior when a channel is busy is you back off. Right? Do you want to transmit a message when the channel is busy? No. There's transmission going on. But in this particular case, why is backing off not the right strategy?
Because C can still transmit, D would hear it just fine and not be interfering with basically.
Yeah.
But wouldn't that interfere with A's transmission to B?
So who is the receiver for A's transmission? B. So what is B receiving? Because that's the only thing that matters, A's transmission. Because the energy coming out from C never reaches B. And the only thing that matters is what...
A, while A is still transmitting.
Yeah, but the only thing...
Interfere then.
So now here's the thing. The only thing that matters is the energy that you receive on your receiver. That's the only thing that matters. Right? So let's think of human voice. It doesn't really matter if there are a bunch of people shouting in other rooms. If the voice doesn't get here, I can still hear you fine. So this is a scenario that's different from hidden terminal. This is called exposed terminal. So the key point here is there is no global view of collision. In a given network, there could be a collision in one node. That does not mean you should stop transmission in all the parts of the network, as we discussed. Key difference between the wireless networks and the wired network is in wired network, the way we've been discussing MAC protocols, there it's feasible for the transmitter to detect the collisions and back off and everything would work fine. But in wireless networks, it turns out that does not work for the reasons that we just discussed. So in that case, how should we redesign a MAC protocol? That's the question for wireless networks. Well, we need to be able to detect if the receiver can hear the sender. That's going to be the most important thing. In wired networks, the transmitter transmits when there is no transmission taking place in the medium. That doesn't work. You're convinced that at least, right? Because we actually need to make sure that the receiver will be able to hear that message. So one approach is for the receiver to somehow tell the transmitters who might interfere with the receiver and ask the transmitters to stop transmitting, right? So that'd be one approach. For example, I need to transmit a message to node B. Node B will tell everyone around it to just be quiet until my transmission is complete. That would be one approach. Would that work or not? I think that would work.
Yeah, but they're going to be telling you to be quiet is also making some stuff.
Yeah, but maybe the receiver will tell everyone to be quiet except me. In which case it might work. Right. So here's one protocol. I think it'll become clear once we go through this example. So basically, the transmitter has to be able to check the availability of channel at the receiver. That is our goal, right? So the way this works is before a sender sends the actual data packet, it actually sends this packet called RTS. I would like to send a packet. I'm requesting a permission to send a packet. And the receiver, and if there is no transmission taking place, or if the receiver does not know of any transmission that will take place in the near future, it sends a response saying clear to send. And then the sender is going to send the data because it received this clear to send packet. So why does this work? Why does this work? And here's why it works. When I transmit a message or transmit a packet to the intended receiver saying request to send, I'm interested in determining if there will be collisions at the receiver. That's what I'm interested in determining, right? Because if there's going to be collision, I shouldn't send data packets. Now, when the receiver transmits clear to send for me with my ID, who else is going to receive that packet? Remember, it's the receiver saying clear to send.
Anyone within range of the receiver.
So all the nodes around the receiver, they're going to receive this message saying permission has been granted for me to send a packet. So what are all the nodes around the receiver going to do now?
Stop transmitting.
Yeah, this would not transmit. So does everyone understand this? This is kind of the key idea here on how we might design a MAC protocol for wireless networks. Does Just to recap, the transmitter, when it needs to transmit a packet, is going to send a request to the receiver. And the receiver is going to say, clear to send for this particular node. And when all the nodes around the receiver, they receive this message, they realize that somebody else is going to be transmitting to that receiver, so they're going to basically pause their transmission if they actually had packets to send to that receiver. This is how we ensure that there is only one transmission that reaches the receiver. Because that's the goal, right? If there are two simultaneous transmissions that reach the receiver, what happens? We have a collision. And we're trying to avoid that. So the receiver says, only this particular node is allowed to send now. And everybody else, they have to keep quiet. So you had a question.
I was just going to ask if the clear to send had to link the time in it as well so that they would know how long they were in the
Yes. Yeah. So when you send a request for permission to send a packet, you say, okay, I have packet that's 100 bytes. And clear to send would also include that information so that the nodes in the neighborhood, they know how long to wait.
Wouldn't that be easy to jam by having something artificially spam clear to send with some invalid node ID?
Yeah, so you bring up a very interesting point. Would it not be easy to jam the network by saying clear to send? Yes, it would be. So you need to do something more. Here's a diagram that illustrates what we just talked about. Basically, when B has a packet to send to A, it's first going to send not the packet directly, but this request. And A is going to say, clear to send to B. But this is wireless. All the nodes around A, they're going to receive this packet. So did C receive this packet? Yes. And what does C know now? Yeah, so C knows that B is going to be transmitting to A, so it has to keep quiet for a while. And how long, that information is in the CTS packet. And B is going to transmit the packet to A, and C is not going to transmit. And we avoided which problem, hidden terminal or exposed terminal? Hidden terminal, right? So even though C is hidden to B, now we're able to coordinate the transmission to minimize the chances of collision at the receiver. Solves the hidden terminal problem. But in practice, we can't completely eliminate that. It reduces significantly the probability of collisions, though. Partly because some of these RTS-CTS frames, they might also collide, right? If you go back to the previous example, what is stopping B and C from transmitting an RTS at the same time? Because they don't even hear from each other. Is there anything stopping B and C from transmitting an RTS? No. All right. Okay, so what are the problems with RTS and CTS? Can we imagine some problems with this approach?
Some nodes might have different transmit powers. It seems like it's dependent on the fact that if you can hear another node, that they can hear you, basically.
Yeah, so this definitely assumes some kind of symmetry in transmit power or transmission range. That's a good point. Yeah. Any other potential problems? So just to elaborate on that point, what that means is when, let's say, the intended receiver transmits clear to send, all the nodes in that transmission range, they're going to not transmit, right? But there could be some other nodes slightly far away that actually have more powerful radio. Did that node receive the packet? Maybe not. But that node is still, when it transmits, because it didn't receive CTS, it might transmit at the same time the transmission is taking place. So it'll be challenging to actually implement schemes like this if we have radios with heterogeneous transmit powers. Any other problems with RTS, CTS? Just think about, I'll give you a hint. If you don't use RTS, CTS, the system becomes simpler or more complex?
Simpler.
It's simpler. And how many packets do we transmit without RTS, CTS if you just had to transmit a packet? Just one, maybe. So what's the, so that should give you a hint for a potential problem with RTS, CTS.
There's a lot of overhead. You have to send 3 control frames for every data frame.
Right, so you need to send a lot of packets to actually send one packet, right? So you're using up the bandwidth to say, hey, I want to send, oh, okay, you can send, okay, did you finish sending? Okay, I finished sending. So you're using up a lot of bandwidth, okay? And we might still lose RTS and CTS. Turns out, Wi-Fi typically does not use RTS, CTS. Some of the wireless access points, they allow you to enable or disable RTS, CTS. So why do they give you this option? Why not enable it by default all the time? For the reasons that we've just discussed. So an assignment for you is when you go home, if you have a wireless access point, go to the control panel and some of these, you'll actually see some of these phrases there, some of these words. There are other ways in which we might coordinate transmissions. For example, we might do time division multiplexing. What that means is different nodes deciding the time slots during which they're allowed to transmit a message. That would avoid this problem of hidden terminal, right? If each node has a distinct time slot during which they can transmit a message, we wouldn't have that problem. So that would be one idea. And another idea is, as someone suggested earlier, we could assign different frequencies to different nodes. And if we do that, their transmissions are not going to collide. Right? So that'd be another way. Here's one way to visualize the frequency band in which the Wi-Fi radios that we're familiar with transmit messages. At the bottom we have .11b channels. A channel is a range of frequencies that are being used to transmit a particular message. So it turns out channel 1 in .11b, we use frequencies starting 2400 megahertz to 2425 megahertz to transmit messages if we're operating in channel 1. There is another class of devices, 15.4 or Zigbee devices. They have narrower channels. But it turns out the channels there, they're going to overlap with Wi-Fi. Right? So that's one way of using this slide to learn something useful. Another way of looking at it is we could actually assign different frequencies to different devices, then we don't have any collision. Let's say you have 2 access points at home and 2 laptops, and you don't want these 2 laptops to have to put up with each other. Because there's a lot of fight going on, saying, okay, you're using more internet bandwidth, you're using more. So what could you do in that case? This will give you the third row, so give you a hint for what you might do in that case, like practically. You might go to your access point and configure one of them to operate in channel 1. Go to the other access point and set the channel to 6. And you go to your laptops and get one laptop to operate in channel 1, another laptop to operate in channel 6. They will never interfere with each other. So we can use this information to our advantage. What is the channel number jump from 1 to 6 to 11 for Wi-Fi? Actually, there are more intermediate channels. They overlap. They're not completely distinct. So if you want non-overlapping channels, those are the channel numbers. And depending on the driver you have on your laptops, these are the numbers that you'll find there. 1 through 11 usually, and depending on the country, you might actually have channel 12 as well. For example, in Japan, channel number 12 is allowed, not in the US. And here's an interesting tidbit for you about channel number 12 on Wi-Fi. So in the US, if you wanted to do experiments in wireless networks on this class of devices, and if you don't want your experimental results to be affected by all the wireless transmissions taking place in the building, so what channels do you use? 26. If you use that, then you can be sure that the results that you are getting from your experiments, they're not impacted in any way by the wireless transmissions through Wi-Fi. Any questions?
Bluetooth uses all of the different channels?
Yes.
All the different frequencies?
Yes. But it jumps between them really quickly. That's the other interesting
So
property
one
of
device would use
many.
a lot of the different channels?
Yes.
Is that why it's so prone to interference?
That's one way of looking at it. But another way of looking at it is also that channel hopping actually makes communication more robust. So let's
Without
say,
interference, you've only got interference on a specific frequency.
Right.
And you're only getting it
Yeah.
when you touch that frequency.
yeah. So that's another perspective to what he just said. For example, there are a lot of devices that are using channel 1. And let's say you configure your device to always use channel 12, then you're in trouble, right? So frequency hopping actually makes your system more robust. But to flip that around, if this device is, in quote, stealing bandwidth from others, if you frequency hop, you don't impact the primary user that much, just once in a while, just to flip that around. Okay, so let's think about the network layer. So we now appreciate some of the problems that are different in wireless networks, and I think we got a concrete understanding of that through our exploration of a wireless MAC protocol, right? Now, thinking about network layer, we usually, so what do we study in wired network when we're talking about a network layer?
Routing.
We're talking about routing, for example, to which node should you send a message if you know the destination, right? We're thinking about network topology, for example. If you think about wireless network, it's kind of interesting because most of the networks are actually single hop. Have you realized that? For example, your laptop always connects to an access point. And the access points are usually put in some corners or in false ceilings or in some hidden locations inside building. But it's usually just single hop. You have a number of devices that connect to a single access point. Right? So there is no notion of multiple hop wireless networks usually. Not commonly. And one of the reasons why we don't have a lot of examples of multi-hop wireless networks is actually turns out it's a very challenging area. And it's a topic of active research. How to get multiple hop wireless networks to work well. But there are some networks that are multi-hop. For example, in vehicular networks that people have been designing, people have been talking about multiple cars talking to each other, exchanging various types of information. That will be a multiple hop network. And there have been these networks called community networks that have been springing up in various cities to share internet access. I don't know if you've heard of them, but they have certainly sprung up in many cities in the US and in Europe. Many of these networks are actually multi-hop networks. Why would you want multi-hop wireless networks? Why would you ever want multi-hop wireless networks?
For one reason or another, wires may just not be feasible.
Yeah, and you might want to extend the reach of your network, right? Let's say you have, two buildings, and they're, let's say, right across from each other, right across the street. You don't want to purchase two different internet services, right? You want to purchase one, and I don't think you're allowed to run a cable across a public street. So what would you do in that case? Maybe in situations like that, you might want a multiple hop wireless network. Let's say you have a wireless access point at home 1, and then you have another wireless device at home 2 that connects to this wireless device, and you have a bunch of devices in home 2 that actually connect to this wireless device that's going to forward all the connections to home 1. So that's an example of a multi-hop wireless network. And there are certainly other examples of multi-hop wireless networks. For example, in the computer lab upstairs on the 5th floor, we have what are called power meters. So we're instrumenting how much energy is being used by each computer, and this instrumentation data is actually sent over multi-hop wireless network. And the reason why multi-hop wireless networks might be useful even in a smaller physical span sometimes is because of obstacles and so many other things that might make it difficult or challenging for one node to communicate directly with another, even when they're close to each other because of obstacles, for example. So in which case it's nice to have this backup route or backup nodes that will relay the information, right? So there's one particular challenge when we start thinking about how to build multiple hop wireless networks, and that has to do with how signals propagate in wireless networks. When a node transmits a message, that message is going to be transmitted at a certain power, and power is going to drop as a function of distance, right? So the farther you go, the harder it is going to be to decode that message. You can decode that message only when the signal is stronger than the noise by a certain amount. It's called signal to noise ratio. Another consequence of this property of wireless propagation is if you're closer to the source of the message, it'll be easier for you to decode that message, or there will be fewer errors, or the probability of packets dropping, and if you want to talk about the abstraction of packets, it'll be lower, as opposed to trying to receive that message from farther away. So what that suggests is not all links are created equal in wireless networks. In wired networks, most of the time we're just using a hop count metric, and that was good enough. But it turns out in wireless networks we have to think about some other factors. For example, how reliable the link is when we're thinking about routing. And here's another property of wireless propagation that we might want to be aware of. That makes it different from wireless links, and the reason why we're talking about these differences is we need to be able to select which links to use when we go from node 1 to node 2 in a multi-hop wireless network. Right? We can't just be using number of hops, it turns out. For example, there is this effect called multipath effect. So you have a transmitter and you have a receiver. The receiver is not just going to receive one copy of the message. It's going to receive multiple copies. This is just like how we hear echoes. When you go to a canyon and say hello, you're going to hear hello multiple times. Similarly, in wireless network, the receiver actually receives multiple copies of the message. Is multipath good or bad? Yeah, generally it will make it challenging to determine what the transmitted message was. Because the signal that arrives a little bit later, a little bit earlier, they'll be very similar to noise. Actually, that'll make it challenging to decode the message. Right? So some links will have a lot of multipath, and some links will not. What kind of links will have no multipath effect? You should be able to think of a situation when there will be no multipath effect.
Over wireless?
Say that again?
You're talking about over wireless?
Yes, over wireless. There's at least one situation. For example, if I have a transmitter here and a receiver at the back of the room, is there a multipath there? There is, because the signal is not just going to go from here to there directly, it's going to bounce off the whiteboard there and also go to the receiver, right? So there's at least one scenario in which there will be no multipath effect.
If it's
And
the
any
same.
space that's empty as far as your range.
Yeah, in free space. Right? If you don't have any obstacles, if you don't have ceilings, floors, walls, physical objects around that'll reflect the waves, then you're not going to have multipath. Okay. So hopefully we understand that the links being different makes the network routing problem also a little bit challenging, right? Because we want to be able to select good links, not just any link. For example, not all the 2-hop paths are going to be of same quality now. That was also true to some extent in wired networks, by the way, right? But here it's going to be even worse, the differences. Or even the difference will be even greater. So the routing problem is, given a source and a destination, you find the best route, and we spent a lot of time talking about various routing protocols. So if we had a way to determine the right link weights, the problem of finding the routes would be very easy, right? If there's a way to basically quantify the quality of the links and encode that as an integer, for example, or some kind of number, then the problem of finding a route would be very easy. But even with that, there is one challenge that's especially unique to wireless network, which is the dynamics. So even if there was a way to quantify the quality of the link, it turns out the quality change over time. But you should be able to come up with a design for this type of problem. You've already solved this type of problem. Do you have a suggestion for how to deal with this problem? If the network is dynamic?
Yeah. Distance vector routing.
You could do distance vector routing, yeah. And one additional mechanism that you might want to use is estimating the quality of the link, and that also has to be done periodically, or it cannot be done just once because the quality of the link might change. So there are routing protocols similar to ones that we studied earlier. For example, destination sequence distance vector routing. We're not going to go into the details of this particular routing protocol. You can look at it and it'll all make sense if you just look at this slide. It's a distance vector routing protocol. Right? And there are a few other routing protocols like DSR, AODV, et cetera, et cetera. So all of these routing protocols assume that we have already determined the quality of the link. Okay, that's a fundamental process that we need, right? So what we will do is next time talk about how to quantify the quality of the links. And the metric that we're going to talk about, it's called ETX. We'll get into the details of that metric next time. So we're